All right, here we go with our third day of optimization problems. We're going to be talking about economics problems later. The warm up here is kind of like the finish of yesterday's stuff on measurement and distance. Determine the area of the largest rectangle that will fit in a right triangle with legs of 7 and 24. And we're going to make an assumption here. And I'm going to set this up with the grass method again. Given the diagram, right, that the triangle is going to, or the rectangle is going to go this way and not parallel to the hypotenuse, right? So we're gonna fit it in, this way. Okay. Um, so that's what we want to do. Where this is x and this is y, we want to maximize this area. Well, how are we going to go about doing this? Well, let's think about a formula. Area equals length times width, or in this case, x times y, right? But what else have we got? Not much. I suppose we have that this would be 7 and 24. We can assume that it's sitting up this way. It doesn't matter. We could flip this thing the other way. But um, how could we get expressions for this? I mean, maybe we want to try and use the Pythagorean theorem or something like that. Certainly we could get what this side is, but there's no distances there. Well, what can we use? We can use our grade 10 stuff. So for instance, this is a line here, and this is part of my brainstorming. It has a slope, right? The slope is down 24, right 7, right? So the line has slope negative 24 over 7. And what's the y-intercept? The y-intercept is 24. So that, therefore, the equation is, well, it's y equals mx plus b. Wow, well, that means I've got my expression that I can put in there, and then I'll have only a function that has an input and an output, just like we need. So therefore, the area is equal to x times negative 24 over 7x plus 24. And then now I can take this derivative of the area with respect to x. A prime at x, this is starting into my solution now, is now that we've got this, it's not that bad because this is just a parabola, right? I'm going to take a step here. Hang on. Take a step. And then that becomes, I'm going to tidy that up so it's nicer. The 2 comes down, negative 48 over 7x plus 24. The maximum, or minimum, I suppose, but maximum occurs when the derivative is 0. So therefore, I've got 0 equals negative 48 over 7, x plus 24. Move the 24 over, a little bit of grade 9 equation solving here. I think I'm going to have 7 gets multiplied, the negative 48 gets divided over there, 2 on the bottom. X is 7 halves. And then what would y be? Well, y would be whatever I get when I substitute back in the line, right? Plus 24, bing, bing, negative 24 over 2 plus y equals 12. So therefore, maximum area, a maximum area of length times width, 42 units squared, occurs when x equals 7 halves, and y equals 12. Okay, Dandy. Now, notice one of the things that we've sort of abandoned is this idea of we should be doing this sort of thing, right? And there's where the derivative is 0, but then what are my endpoints? Well, what are the possible values for x? And I should have my endpoints. Well, x could be 0, or it could be up to 7, right? So I should check my endpoints, but often my endpoints give me zeros, and these will be the minimums, and then whatever this is, where the derivative is 0, is going to give me the maximum. So I have abandoned that a little bit, but I'm not that ashamed of myself for doing that, since it's often 0 on our endpoints that are in there. All right, great. Let's get into the business stuff, and for some people this will be right up your alley. For anybody who's going into business, um, you'll recognize these types of questions. Solve optimization problems drawn from a variety of applications, including real life. Uh, the tour bus has 60 seats. The maximum possible ticket price is $10, but the tour manager can sell 10 more tickets for each dollar she cuts from the ticket price. So the idea is you cut the price, you can maybe get some more people to show up, right? What should the ticket price be to maximize revenue? What is the number of seats, what's the number of seats, if any, will be empty? And then, we can plan accordingly. So here comes the solution. What am I given? Let's state some things. The bus has 60 seats. Price is at most $10 a seat. So what does this mean? So I've got this, if I'm thinking about the number of seats, this is automatically gives me a couple of constraints I can think of. I was talking about the endpoints, right? If that matters. What's required? We want, what should the ticket price be to maximize the revenue? So we want the ticket price for the maximum revenue. So when we see that we want to maximize revenue, we need a revenue function. So at some point in our analysis, we need revenue equals and then some sort of function. How we get that, we're going to have to worry about that. Well, what's revenue? Revenue is just the number sold times the price for one, right? That's the revenue. And so what do I got? I'm calling S the number sold and P the price. So I've got revenue equals number sold, which is S times the price P. But we kind of want one independent variable, right? We need S and P in terms of some independent variable, maybe in terms of each other, but who knows? Well, the key is here, for every dollar cut, stuff happens. So why don't we let X be the number of cuts? So then, what's the number sold? Well, the number sold would be just be for every time she cuts the price, she's going to sell 10 more tickets. So that's going to be 10x. I suppose if she didn't cut the price at all, she'd sell 0 tickets. But then what's the price? Well, it was $10, but for every cut we've subtracted $1 off there. So then I can get a revenue function, right? So then the revenue in terms of X is 10x times 10 minus X. And now this is an easy function. Just multiply that out. It's a parabola of some sort. And then I can take the derivative. Take the derivative and I get, by the way, that is called the marginal revenue. And if I had a cost function, C prime at x is called the marginal cost. For some reason in business, when we take the derivative, it's called the marginal. Good to know, I guess. Well, maximum revenue occurs when r prime at x is equal to 0. 0 equals, looks like 5. Bing, bing, bing. 100 on the other side divided. All right, dandy. So then, what do I got? Well, there's the one that I want to investigate, the revenue there. If I put that back into the formula, that's just going to be 500 minus 250 is 250. Well, what are the endpoints? Notice if I look back here, then I can see my constraints. My constraints were the number of tickets has got to be less than 60. Well, that means X has got to be less than 6. And also, if X is less than 0, that doesn't make any sense, right? I can't. It says the maximum ticket price is at most $10. If X was negative, I'd have a negative number of people going, and then my price would be more than 10. I could have X as being as low as 0 and as high as 6, and I can calculate those endpoints, and I see that the maximum revenue happens here. So what's my conclusion? A max revenue of $250 occurs when the cost is price equals 10 minus 5, $5 tickets. B. The question B was what number of seats, if any, will be empty? Well, number of seats sold is just 10 times 5, which is 50 seats, but we had 60 on the bus. There are 60 minus 50 equals 10 empty seats. And so what will we do with those? Well, there might be some way to squeeze a few dollars over the out of those extra seats. Okay, I am going to stop there and pick up the rest of this lesson in part 2.